if you'll see that there is enough interest, and we will install the software in the computer lab across the hall, so you guys will potentially be able to go over these online trainings and also work a little bit on the software. Again, it's potentially not for everyone, but for those of you who may be interested in pharmaceutics, pharmacokinetics, maybe later on going into research, clinical, preclinical, working with a pharma company, having something like that on your CV can be helpful. You can get certificates for this type of thing. So yeah, let me know. Okay, now moving to our lecture. So in the previous lecture, we talked about the simplest way from the pharmacokinetic point of view to administer drugs, and we defined certain terms on how to calculate some of the parameters, and then also on how we can apply those parameters for calculating concentration of the drug in the body. So that's really, as pharmacists, we'll be interested in understanding what is the time course of concentration of our drug in the body. Now, while intravenous bolus administration has certain advantages, it's not suitable for all drugs or all situations. So another way to administer drugs is to administer them at a constant rate regimen, and specifically we'll be looking today at intravenous infusion. So again, the drug is directly administered into the bloodstream, so we'll be bypassing any type of absorption barriers. Again, that we'll discuss this in other lectures about extravascular administration. However, here is intravenous infusion. Instead of having our drug injected into our bloodstream instantaneously and achieving very high concentrations, we will be connecting our patient to an infusion pump or hanging the bag with an infusion solution, and it will be dripping slowly into our body. Okay, so what actual objective for this lecture? We will talk about this type of administration and we will define new terms. For example, steady state concentration, rate of infusion, and we'll also learn what controls, again, our concentration in the body. So there are several parameters that will be controlling the time course of concentration and the overall profile. We'll see how rate of administration or concentrations at steady state at the plateau level will be controlled by various pharmacokinetic parameters. Also, we'll discuss a combination of IV bolus administration and IV infusion administration. Sometimes our therapeutic goals cannot be achieved by one or the other, and we have to combine both of them. And again, there will be some calculations that we can perform, including calculation of the loading dose. Loading dose will be something that we administer as a bolus to match our infusion profile. Now, sometimes pharmacokinetic data are not available from IV bolus administration for certain reasons. For example, drug can be very toxic at high concentration, so you can never inject it as a bolus. By infusing it, you're avoiding these high peak concentrations, and some of the data that you derive from those profiles basically can leverage those data after IV infusion to calculate again pharmacokinetic parameters of interest. Use them after that, again, for optimizing our drug delivery. Okay, so moving to our profiles. The profile on the left-hand side, you should be able to recognize. This was a signature profile for intravenous bolus administration. Concentrations are very high at the beginning, and then they fall this time to lower concentrations. Again, we will now discuss just one compartment model, where with every half-life concentration will be dropping, and if you plot this on a Severlov scale, you'll see a straight line. Now, in case of the infusion, again, you have a bag connected to the patient, and then you regulate the infusion rate, such and such number of drops per minute, or maybe milligram per minute, depending on the concentration of the solution. So at time 0, your concentration will be 0. There's nothing left in the patient. As you keep infusing, concentration will start climbing up. This for a long time, and we'll talk about it. We will reach the situation which we'll call steady state. The rate of drug input will be equal to the rate of drug output from the body, and therefore concentration will become stable as long as you infuse the drug, your concentration should be at the same level. Once you stop the infusion, here concentration will start dropping down. Now, again, in future lectures, we will also talk about extravascular administration. For extravascular administration, the profile will kind of similar in a way that concentration at the very beginning will be 0, and then it will start to increase, and then it will go down. Now, depending on the length of the infusion, sometimes just by looking at the profile, it would be impossible to say if the drug was administered as an infusion or as an extravascular dose. Right? If you see this concentration reaching a plateau, and then it moving down after infusion or drug administration was stopped, it indicates to you that it potentially was an IV infusion. But both of these, infusion and extravascular dose, will be characterized by this point at the very beginning concentration appears. The drug was administered to our patient before. So let's, before going to PK calculation, discuss some advantages and disadvantages. Intravenous infusion allows us very precise control over concentration. We can measure potential concentration of patients and adjust the rate. We can also adjust rate based on condition of the patient or patient body weight and so on. It allows us to maintain drug concentration at a constant level. Again, if you infuse the drug for a sufficient period of time that we achieve the steady state, basically the concentration will be very, very stable. We don't have fluctuations. Concentration won't be going up and down. This might happen if you administer drug as multiple administrations, multiple injections, or multiple oral dosage forms, where concentration going up, going down, going up, down. In some therapeutic situations, you need to really maintain concentration at a very stable level. As I mentioned in the first lecture, some drugs, we have, these drugs have a very narrow therapeutic window. Who remembers what therapeutic window is?
The range between the effective, the minimal effective concentration and the minimal concentration.
Right. So the therapeutic range of the drug, therapeutic window, will be difference between concentrations where below minimal effective concentration there is no effect, and then at the upper level, upper threshold, beyond that threshold, the drug will become highly toxic. For some drugs, it can be very wide window. For some drugs, it can be just change of 2 or 3-fold in concentration. They bring you from the drug being non-effective to drug being toxic. Now, administer something like that as IV boluses or oral doses and maintain concentration in that window can be very, very quick. But it can be achieved relatively easy with constant infusion. Now, this type of administration is also quite suitable in critically ill patients where you need, again, fast control over these concentrations. For example, if you give patient a tablet, initial concentrations are low, then they're increasing. However, as long as you have the dosage form in your gastrointestinal tract, there's a drug inside your gut, it's keep being absorbed. So what happens if you suddenly see toxicity for such a drug? You can't really do much because the drug is still in your system and it will take time, it's being absorbed, so concentrations may still go up even though you already know that you don't want that drug in patient body. Now in case of infusion, basically the moment that you close the infusion line, the concentration starts decreasing immediately. Right? You have way more control over it. Now, we mentioned that sometimes it is desirable to reach your therapeutic concentrations very fast. In this case, we can combine bolus and IV administration, and I'll show you examples and the way to calculate, for example, loading dose. Now, one of the main disadvantages, of course, for this type of administration is that it's mostly reserved for inpatient settings, right? And also, you have, as long as you have this infusion, you have a continuous open intravenous access, right? So you have a line, you have a needle, or a catheter is going into patient arm, and that can be a source of infections. If you have a patient that is treated over many, many days, it can become a problem. So as soon as you can switch a patient from intravenous dosing to any type of other administration, This slide just illustrates, gives you some names that you may have heard from other drugs and examples of drugs that can be delivered as intravenous infusion. So we'll just move on from there. In the previous lecture, again, we mentioned that when we only talking about elimination of the drug from the body, for most drugs, we'll be talking about this source order kinetic, right? We looked at this differential equation down here, dA over dt, equal to minus k multiplied by A. Elimination rate of the drug from the body was dependent on how much drug we had left in patient's body. And then what it dictates was that basically with each half-life, concentration will grow by half over time. Now, one of these more rare examples where we're dealing with zero order kinetic is intravenous infusion. Now, in this case, we're not talking about drug being eliminated from the body, we're talking about the drug entering into our body. So that process is not dependent, as I mentioned before, on how much you have left in that infusion bag. The patient can be connected to a small infusion bag, large infusion bag. However, we dictate the rate of infusion. This will be 0 or R infusion and some other caps. So this will be the actual rate, number of milligrams per minute that entering patient's body over time. So now we can work with a little bit more elaborate schematic. So this, remember we said that represent a compartment. We're talking still about one compartment model. At the end of the lecture, I'll have one or two slides showing pharmacokinetic behavior after intravenous infusion for two compartment model distribution. But for now, again, we're focusing on one compartment. So we'll have this single compartment with model distribution. They have a clearance process. This is exactly what we had before. However, now we have a continuous input over time, for which again, usually people use K0 or R infusion. Now, this K0 R infusion will be zero order rate constant. That zero order rate constant is different from the rate constant for elimination. It's very different in a way that it has different units. What were the units for the rate of elimination? Okay, yeah. What are the units for the half-life? Time. Right? Unit for the half-life is time. Now, if we calculate KEA as 1 of 2 divided by the half-life, then the units of the elimination rate constant become 1 over time, right? Or time raised to the power of -1. Okay? Now, here we're talking about different units. These units here are amount per time, so milligram per minute, or grams per hour, something like that. So it's a different rate. Now let's define more things in this specific profile. So again, you start from your concentration at time 0, you switch on the infusion at a certain fixed rate over time. Concentration is very enough. If you continue infusion for sufficient period of time, you will reach this situation where we define it as a steady state. Right? So rate of input will be equal to the rate of output. Sometimes we also call it a plateau concentration. Right? So concentration increasing over time and reaching a certain. Once you stop the infusion, the drug will start to eliminate from the body. And what will be important here that once you stop the infusion, all these molecules inside your body, they have no idea how they reach the body. If they go administered to the bolus, or they go receive through the infusion, or maybe even from the oral dose. The molecules inside the body don't know. So once you stop the infusion, all this drop will be controlled only by your volume of distribution and clearance properties. Right? So the elimination after the infusion was stopped, controlled by exactly the same factors that we discussed last time. Clearance and volume. Now, what other things we need to define here? Duration of the infusion. Right? Switch the infusion and go on for some period of time. Either you reach the steady state or you stop the infusion at an earlier time point, maybe even here. That time that you infused that drug was the duration of that specific infusion. Now, what is also different here, for IV bolus, we define dose in just milligrams or nanomoles. So it was at one number. Total dose administered instantaneously. In case of the infusion, the dosing information is given by two numbers. It's duration of the infusion and the rate of the infusion. So it's time and how many milligrams per unit of time. For duration of the infusion, it will give you the total dose. So the information can be provided two ways. Either infuse for 20 minutes at 1 milligram per minute, for example, or the information can be provided to infuse 20 milligrams over 20 minutes. Right? So total dose, 20 milligrams over, say, 20 minutes. You need two numbers for any type of this calculation. Only then you will have full information about your dose. Any questions? Okay. So now let's create our new pharmacokinetic equation that describes that specific profile of concentration going up during the infusion. Again, we're talking about one compartment model. Who can give me some of the properties of one compartment model? Volume is constant over time. What else? Drug distributes homogeneously through that single compartment. Okay. What else? Elimination starts immediately with dose administration. Okay. We have some others, but that's the main thing. So our drug is injected immediately. Immediately elimination starts. Drug distributes homogeneously through a single compartment. Right? Remember, it's all the approximation, but the useful approximation for our calculation. So before we had this equation of dA over dt, amount. The rate of change of the amount of the drug in the body, we only had that part, minus k multiplied by a. So that is the part that is responsible for the elimination of the drug. However, now we also have an additional rate constant in this equation. So we have this k0. Now over time, we have both input and output that may be happening simultaneously. And so we have two components in our differential equation. Now k multiplied by a, of course, can be rearranged as clearance multiplied by t. And it's k multiplied by a is volume distribution multiplied by concentration, and then k multiplied by volume gives you clearance. So this differential equation of rate of change of the amount of the drug in the body over time can be written both ways, with amounts or clearance and concentration terms. Now, similar to IV dosing, we cannot really do much with our calculators if we need to calculate things using this differential equation form, so we need to integrate it. And if we integrate that equation, this will become our operational equation for the amount of the drug in the body during the infusion. It looks more complicated comparing to what we had for IV bolus. What we have here, we have k0 divided by k. So the rate of our infusion divided by the elimination rate constant k. And then in parentheses, we have 1 minus e raised to the power of minus kt. So this k and this k is the same k, elimination rate constant. E stands for time. And similar to IV bolus, we can also rearrange that equation. We can divide both sides by the volume and derive to more useful equation for us, where we're describing concentrations over time. So C will be equal to K0 divided by clearance. Or instead of clearance, we can put a K multiplied by volume. And again, in parentheses, we have 1 minus E raised to the power of minus K. This equation gives you this type of signature profile shape. Start from time 0, so if you put 0 in here, concentration will become zero, and then over time it's going up and up and up, and it will stabilize at some point. So defining this steady state concentration is very important for us from the therapeutic point of view, because that's why we usually use this infusion type of administration. We want to reach steady state concentration. They are not changing over time, and we have very good control over it. So you can define this using two approaches. One approach is just looking at this equation and saying, okay, if you infuse the drug for a very long time, you don't know yet for how long, but just if you keep infusing, eventually it will reach that steady state level by definition. So if you put into this equation instead of t, basically time infinity, this whole term of e raised to the power of minus k multiplied by very large number, right? This e raised to the power of minus k times infinity becomes 0. And again, basically by definition here, concentration at C at steady state, so CSS as we call it, will be equal to K0 divided by clearance. Okay, so if you just put this very large number of hours in the equation, that term becomes 0, and then it's K0 divided by clearance multiplied by 1. So concentration at steady state is K0 divided by clearance. In parallel, we can also define amount of the drug at steady state in the body. So in this case, we multiply both sides by the volume, and volume can cancel out from the clearance term, so it will become K0 over K. Okay, so what this already gives us that if we know the clearance for the drug, and we know what kind of therapeutic level we want to achieve, we can easily calculate the infusion rate. Know clearance of the drug from the literature, and you know that you need to get, for example, 8 milligrams per liter for this drug to be effective. You can calculate K0, is what rate you need to input the drug into the system. There is another way to get you to exactly the same equation. So this, based on our definition of the steady state of the situation where the rate of input of the drug into our body is equal to the rate of the output. So when the rate of input is equal to rate of output, concentration is not changing. So if we saying the concentration is not changing, then dA over dt is equal to 0 by definition. Okay, so and then if we look at this differential equation on top, if this is equal to 0, then K minus clearance multiplied by C is equal to 0. And if you rearrange, you arrive into exactly the same equation for your constant dosing regimen for intravenous infusion. So CSS is equal to K0 divided by clearance. We will use this equation a lot in today's lecture and calculation. On the right-hand side, you also have your units. And so that can help you make sure that you're using the proper equation. So CSS will be defined in terms of concentration. So for example, milligram per liter. Okay. Now we know that clearance is defined in flow terms, for example, liter per minute. And then K0, it's not 1 over time, it's units of mass over time, milligram per minute. And if you divide in milligram per minute by liter per minute, minutes cancel out, and you get milligram per liter, which is exactly the units of concentration. Okay? So everything in your equation should balance. Suddenly you're calculating something and your units become very strange, so if you by mistake try to use K here, your units won't match. Right? If you put here something like just elimination rate constant, it will be 1 over minute, and then things are not canceling out, and you're not getting to the proper units for your concentration. So keep that in mind. So the drug gets into your body through the infusion line, and then being eliminated through the kidneys and the liver. Yeah, basically your clearance. Right? Other questions? slides will discuss two important properties of IV infusions, and some of these can be a little bit counterintuitive, so please follow my explanation carefully, like try to focus on this. We will have two questions that may be asked. What controls how high your steady state is, and how fast you can get to those steady state concentration? Okay? And intuitively, sometimes we will think, okay, if you need to get to our steady state fast, if you start infusing very fast, you'll get there. And this will be the wrong thing. Through looking at the equations, and I'll try to explain it, you will see that the amount of time that takes you to the steady state is not controlled by the rate of the infusion. It's only controlled by the half-life of the drug. And what the rate of the infusion controls is how high you go with your steady state. So let's try to look at this. Here we have a default infusion with the rate of R. Now, if you'll infuse the drug at a twice that rate, 2R, we'll get at a twice high steady state. And why it happens? It happens because, you look at this equation in the previous slide, we derived it. Concentration at steady state is controlled by the rate of the infusion. So the concentration is directly proportional to the rate of the infusion. And then it's also controlled by clearance. But in case the clearance of the drug is stable, which is in most cases are, if you're talking about patient in a specific situation, right, in a specific patient, not different patient, that specific person will have a specific clearance. So if we need to calculate concentration at steady state, we will know the clearance, and then concentration at steady state is directly proportional to that rate of infusion. If instead of K0 I have here, if I triple the rate, concentration at steady state will triple. Now, you also don't see any mention of the half-life of the drug in this equation. Right? It says is independent of the half-life. Not multiplying, not dividing, not adding. There is no half-life. So, the higher we go with concentration is not dependent on the half-life. It's only dependent on the rate of administration. Okay, hope I convinced you. And now, if we accept that, right, then again, we can look at the equation if you guys are not convinced. Concentration at steady state directly proportional to rate of administration. We can have such statement as shown, for example, here. For all drugs infused at the same rate and having the same clearance, the steady state concentration will be the same. Okay? Something like that can be part of your exam or a homework assignment, right? Why this will be true? Basically, we're saying two different drugs, if they have the same clearance, and if they infused at the same rate, they will reach exactly the same steady state. Right? Even if one drug has a half-life of 1 minute and one drug has a half-life of 1 month. Again, half-life is not a part of that equation. So as long as the clearance is the same, infusion rate the same, concentration at steady state will be the same. However, we cannot make exactly the same statement about the amount of the drug in the body. Okay? Why is that? On the slide, right? Amount of the drug in the body at steady state is concentration at steady state multiplied by the volume. The fact that two drugs have the same clearance doesn't mean that they have exactly the same volume of distribution. So I can make a generalization like shown in that sentence, that two drugs infused at the same rate and having the same clearance will reach the same steady state concentrations, but it won't be correct for amount of the drug at steady state. And there will be only one case when it will be true. If these two drugs have exactly the same clearance and exactly the same volume, then they will have exactly the same amount of the drug at steady state between them. Any questions here? to, hold on. So how high we go with concentration is one important thing, right? These are the concentration levels we want to achieve. However, it can also be important how fast we get there, because oftentimes we need to achieve therapeutic concentrations relatively fast. So if you have two drugs that you may infuse, and you want to achieve a specific steady state fast, you would want to select a drug with a shorter half-life. Because what we can see from our equation, that reaching the steady state is only controlled by the half-life. And to demonstrate that, we will take our equation of concentrations over time, that is shown here in the gray box, and that's the one that we derived 2 slides ago, same equation, and we just rearrange it. We rearrange it in the form of percent of the steady state. So concentration is on time, we divide both sides by C steady state. So C over C steady state gives us a fraction of steady state that we already achieved. Now what is left on the right hand side of that equation is 1 minus e raised to the power of minus kc. And to demonstrate it even better, we're doing the same rearrangement as we've done for isochorus, where we present time instead of in units of time, in numbers of half-life. And so we rearrange e raised to the power of minus kt. Instead, we're using number of half-life, that's t divided by t half, in which case e minus kt becomes 2 raised to the power of minus n. Exactly the same derivation as we've done in the previous lecture. So what happens here is, on the left-hand side, we have a fraction of the steady state that we've achieved over time, and on the right-hand side is number of half-lives that plays a role in the calculation. So if we'll introduce here time 0, so 0 half-life, 1 half-life, 2 half-life, 3 half-life, and 4 half-life. Here are the calculation that you can perform yourself, or just look at the table. At time 0, no time has passed yet. We at 0 concentration, so 0% of steady state. So I'll put here 1, it becomes 50% of steady state. After 2 half-lives, 75% of steady state, then 87.5, and so on. So for any practical purposes, when we reach 90 to 95% of the targeted steady state concentration, it should be enough for therapeutic purposes. Okay? Because again, whenever we do pharmacokinetics or any type of scientific measurement, there is always an error associated with that. So even when we're doing pharmacokinetics and we're doing very much validated methods for measuring concentration, even the FDA allows you plus minus 15% error in your measurement. Okay, so for any practical purposes, reaching 90 to 95% of steady state concentration is good enough for therapy. Now, if you look at these numbers, resemble what we've seen for the elimination of the bolus. Right? After 1 half-life, 50% leave the body, and then after 2 half-lives, we only have 25% remaining. So that table here is actually complementary to that elimination part. I'll show you an example of that again. Okay, I want to introduce also another pharmacokinetic parameter that you might see sometimes in pharmacokinetic literature or reported in drug information databases. It's called mean residence time. We won't go into detail because you will have a separate lecture that talk about some non-compartmental approaches for analysis of the data. That's where we derive this mean residence time parameter. Just for now, by definition, mean residence time will be equal to amount of the drug at steady state divided by the rate of infusion, and it represents time that the average molecule stays in the body. It's a little bit confusing, but what is important here that MRT, like if you, again, replace this A steady state by A0 divided by K, you'll see that MRT is equal to 1 over K, which K is familiar to you, it's elimination rate constant. Okay, then we can ask a question, what is larger, MRT or the half-life of the drug? For example, exam question, we have to say, what is larger, MRT or the half-life? Now we know that the half-life is ln of 2 divided by k. MRT is 1 divided by k. So MRT is actually in fact larger, and specifically it's 1.443 times the half-life. So that's the relationship. MRT can also be calculated as volume divided by the clearance, again through the relationship with k. I'm connecting this to your future lectures, but just it was important to mention it here because we already talked about some amount of the drug at steady state. So for now, we derived the equation that describes concentrations in the body over time of the infusion. So as long as the infusion is happening, concentrations are increasing. After approximately 4 or 5 half-lives, we reach effectively steady state. And as long as you keep infusing the drug and the clearance doesn't change, concentration won't change, right? This is our equation. Now, we also need to know what happens once we switch off that infusion. Basically, we describe what happens up to here, and now we need to understand what is happening once we switch off the infusion. This is a linear representation. So at this point, I want to introduce capital T parameter, which will be the duration of the infusion. Here we used small t, which was a changing parameter over time. Right? Time was changing. Now, capital T is the duration of the infusion. For example, in this case, if you look at this picture, the infusion was for 24, I'm not sure what it is, for example, hours, right? Units of time, 24 units of time. So if you want to define what was the concentration here at the moment we stop the infusion, what we need to do, we need to use this equation and basically put, instead of small t, capital T, so CSS multiplied by parenthesis 1 minus E raised to the power of minus A capital T. So if you know the elimination rate constant and you know the CSS, you can calculate what was the concentration at the moment we stop in that infusion. Right? Now, of course, that concentration will be equal to CSS if you infuse for long enough. However, the same equation will apply if you want to stop that infusion at much earlier times. So for example, if you just infuse for 3 hours, it won't be correct to say that at the end of the infusion you reach the steady state. Calculate that, you need to really input here 3 hours and calculate it number. When we're speaking and talking about that specific point, because that point will anchor the future elimination of the drug. As I mentioned, once you stop the infusion, all these molecules will start eliminating based on volume distribution and clearance of your drug from the body. So all these molecules, at that moment, if you stop the infusion, there is no more input, and they have no idea how they got it. So after 1 half-life from that point, concentration will be half of that initial value. 2 half-lives, 25%. So again, we're talking about 1 compartment model here, the simplest case. So that is easy, 1 half-life, 2 half-lives, but if you're interested in exactly specific point in time, what you need to do, you need to apply this equation shown. Okay, what we have it, concentration after stopping the infusion will be equal to concentration at that specific moment that you actually switched off the infusion. So C at duration of the infusion time that we calculated before, multiplied by E raised to the power of minus K multiplied by T tab. What is T tab? T tab is the time that passed since we stopped the infusion. So we're basically shifting our time scale. T tab can also be expressed as actual time minus the duration of the infusion. So to give you an example, at 36, let's say, hours, what is the T tab? 12 hours. We infuse the drug for 24 hours. So at 36 hours, our shifted time scale shows only 12 hours. So for example, if the half-life of this drug is, let's say, 6 hours, and we know that concentration when we stop the infusion was 1, what will be the concentration after 12 hours? We're starting from 1 and 2 half-lives pass. Quarter of the concentration. After one half-life, half of that initial value, and then after another half-life, half of the half. So 25%, and in this case, 0.25. Calculate it properly in this equation, so if it's not on an equal half-life intervals, you basically just put the numbers here. If I would need to calculate it in 35 hours, I just put T at 35 minus 24 as the duration of the infusion. Any questions here? Okay, so let's take it a little bit further. We derive pharmacokinetic parameters from published studies. So we do the studies ourselves. Sometimes we don't have all the information. So if this was the actual profile after intravenous infusion for, let's say, 12 hours, and your whole experiment lasted for 22 hours, if you collected both phases during the infusion and then after infusion, you have the full profile. But sometimes you don't have all the information. Sometimes the study is done just during the initial period of the infusion, and sometimes study is done only once you stop the infusion, for various reasons. For example, if you're doing study in a pediatric patient, oftentimes you cannot take as many blood samples. Characterizing the full profile, you may need 10, 15 time points. If you take in pharmacokinetics in a small baby, for certain reasons, you may not be able to take so many blood samples. And so you may be limited to a certain set of information. So therefore, I'll show you two ways to calculate elimination rate from PK data during and after the infusion. So if you look at this data table, here are the times from time 0 to 24. These are all time points, and this concentration column, actually, these are the numbers that we measure. Okay? So concentrations, milligram per liter, time in hours, this is our actual measurement. However, we will also do two treatments of the data. So first, if you know that the infusion only happened for 12 hours, we will need a secondary column that we'll call time post-infusion. Okay, so this will be T minus capital T. 14 hours, if the infusion lasted for 12, this is 2 hours post-infusion, 16 hours becomes 4 hours post-infusion, etc. Now, for one of the calculations, we also need to calculate, we need not the actual concentrations, we need the difference between the steady state and the measured value. Okay, so if we infuse the drug, and we'll see on the profile that we're reaching the steady state concentration, if the concentration is not changing significantly, we can assume that we reach steady state. So keep looking at these numbers. Concentration was 3.3, 5.4, 7.6, 8.7, 9.3, 9.6, 9.5. So we see that toward the end of the infusion, really concentrations stop changing. 9.6, 9.5, 20 practical purposes will be exactly the same number. So what we need to calculate here is the steady state concentration minus the concentration that was measured at that time. If we do that, so for example, we'll take 9.5 as our steady state concentration, minus 3.3, this will come 6.2. 9.5 minus 5.4 is 4.1. And that's how we're creating this secondary column of data. And we'll use it for one of our calculations. Okay, so we can plot our data two ways. here I'm assuming you have this full profile. We can only use post-infusion data, or we can use during infusion. So if you're using data during the infusion, this will be this red squares and red line. Basically, again, you will plot your numbers on the semi-log paper and you will create the regression line. If you're using data during the infusion, you need to plot this CSS minus C versus actual time. Okay, so for example, 1 hour, concentration was 6.2. At 2 hours it was 4.1. At 6 hours it was a little bit less than 1, so 0.8, 0.2 here. Okay? So you plot those numbers, and then you create the regression line. When you create the regression line, the slope of the line will be your elimination rate constant, and the intercept will become CSS. So during the infusion, this is what you plot. Okay, so ln of CSS minus C, and then intercept is concentration at steady state, and the slope is your elimination rate constant. Any questions? Okay, you will have a homework to try to do it yourself and then maybe become more clear. Yes?
So you said that the initial number that inclusion for the line is steady state. How are they to?
So if you continue, if you bracket